Hey everyone, welcome back to Remote Sensing Pro. Today we will classify Landcover using Gaussian Mixture Models, GMM, and we're going to do that on the Landsat 8 bands. GMM is like a smarter K-means, I would say, because it lets clusters be elliptical and also gives probabilities. We're going to train GMM, map the classes, and finally compare the result to a true color image. If this helps, please like, share, and subscribe. All right. Now let's look at how Gaussian mixture models work in practice. First off, each of these blue dots, see these dots here, are like pixels from our image, our satellite image. And they are plotted here with two features, feature 1 and feature 2. You can see they naturally form groups, like somehow they're already grouped on their own. So we have the solid black ellipses, 1, 2, and 3. So these ellipses, the solid ones, show the 1 sigma region, meaning most of the points in that cluster fall inside. However, we have the dashed ellipses, these black dashed ones, another 3, 1, 2, 3. These are the 2 sigma, which cover almost all of the points, pretty much. Unlike K-means, which only makes round clusters, like we saw in the last tutorial, GMM lets these ellipses stretch and even tilt just to fit to the data's shape. Finally, look at the curved contour lines in the background. These contours, right? These show the model's probability surface, where it believes points are most likely to appear. So in short, GMM models each clusters as a Gaussian cloud with its own center, its own shape, and even softer boundaries that overlap. And that's why it's more powerful than K-means when our Landcover classes are irregular. Take, for instance, where we have clear water and turbid water. Okay, I hope this makes sense. Now let's dive into coding. First, we're going to have a recap of band preparation, just the way we did it in tutorial 9, the last tutorial. We're going to start by importing our data. So we're using this asterisk here to import all the band files in the folder. I'm going to run this code. Okay, so I see we have band 2 to band 7. Just in case your bands are not in order like this, 2, 3, 4, 5, 6, 7, if they're just like messed up, you want to sort the bands first to ensure they're in order before you stack. And to do that, you want to do just sorted. And run the code again. So it's going to help you sort it if it's not already sorted. But mine is already sorted, so no issues, just in case. And one other thing is, if you don't want to view all of these listed bands, you just want to know the number of bands you have in the folder, you can just go ahead and view the link, LEN, and that's going to tell you the number of bands you have. And for us, we have 6 bands, 6 number of bands in this folder. All right. So go ahead to the next one, which is to create this array and then convert the bands to float 32 before we start them. So the first thing we're going to do is creating this array that is going to hold each of the bands as a 2D, remember? And we use the first band we have in the folder to georeference the rest of the bands. So this first band, which has the index 0, is going to be our reference band, and we're going to use it to georeference the rest. The first being transformed is to map the pixels to map coordinates. And then the second is to copy the coordinates reference system, the CRS, and then get the shape, I would say dimension, height, and width of the same first image and use it to ensure that the rest are in order. After that, we're going to read the bands and then convert to float 32. This is actually good for save math. I have to bracket it here. And finally is to stack. So for our stacking, we are stacking rows, columns, and number of bands. And so we're having rows, columns, number of band. That's going to be our shape when we print this shape right here. Let's go ahead and do that. So we have our rows, columns, number of bands. So this is more like the height, the width, and the number of bands we have. All right, this is ready for us. Next is to filter or somehow to normalize the bands, right? So want to keep only pixels that are finite across all bands. We don't want any infinite values in the pixel. And also we don't want invalid ones like the NaNs, right? So want to use numpy.isFinite to get rid of all of those and only keep the ones that are valid for us, and we're going to name it valid. And this is going to do that within these 6 bands here, the axis 2. After that, we're going to reshape to a 2D table. Since we have a 3D here, we want to reshape this 3D into 2D because we want it to be in 2D before we run the model. And then we'll also ensure that we're flattening this 2D that we just created here, this mask that we created here. We want to flatten it to 1D and finally use it for our final 2D feature table. All right. So the next thing we want to do is to standardize. So each band contributes fairly. We're going to do that using this z-score. And we're going to get one mean for each of the bands. And we're going to have a standard deviation. We're going to have one z-score as well. So that's going to be our final result, which is xz.shape. All right, this is just a recap of what we did earlier in the last tutorial. You may want to check our last tutorial for more details. All right, I'm going to run this right away. Awesome. So you can see here we've just finished everything and see how our 2D feature table, which has the pixel and also the band. So we converted everything from rows, column, bands to the number of pixels as well as the bands, number of bands. Awesome. All right, so now let's move to the next one. So the next thing we want to do is to set up model. We're going to set up the model and then we're going to run it on the standardized data. First of all, we need to import the model we want to run, which is the Gaussian mixture. We're going to do that by importing it from the Scikit-learn mixture. And the next is to create the number of classes. Remember, during the k-means, we chose 5, and that's why I just want to keep it 5. You can always do any number of classes that works for you in your study area. And so just for the purpose of this video, I'm going to keep it 5 classes. And our GMM is going to be our Gaussian mixture that we imported. I'm going to create this. The first is our number of components, which is the number of classes we have here, which is 5, more like our K, right? And then we have the covariance type, which we are going to set full. I commented this here because it's very, very important for us to understand why we're using full. This is just for us to have each class for its own shape or orientation. And then we have the random state as 42. However, I'm going to keep the number of initialization today as 5. When we did the k-means, we used 10. Today, I'm going to use 5 because it really takes time for this model to run. And So if you want more stable result, you can go ahead and do 10 or even 20. Sometimes there was a time I ran 100. So I just put 100 here, left everything, went for lunch, I came back. So I'm going to just do 5 to make everything quick and simple for us today. All right, so I've run this model. I'll go ahead and run this one right away. Let's see. All right. Next is to now train the standardized valid pixels. So we've got our model set up and we're going to train this model. So we're going to do that on the standardized data, the pixels here that we've done everything we wanted to do on. Now it's just to train the model on that pixel. Let's go ahead. So after we've trained the model, we want to use it to predict, right? And we're going to call it level GMM. So we're predicting on these same valid pixels. So we're not changing that anytime soon. So we're going to run that as well. And so next is to put the labels back into image shape. So just like we did, once you're done with everything you want to do, you want to convert it back to the image shape. And that's going to have the rows and the columns, right? Initially, we've got like the pixel, number of pixels and the number of bands. We want to convert it back to the rows and the columns. This is very important because that's how we're going to be able to view or visualize the result. So that's what we're going to do right here. Let's run this as well. Okay, so you can see the model is still running and sometimes it takes a lot of time. So I'm going to come back once this is completed. All right. Okay, we're back. The model is completed. You can see our Gaussian mixture model ready. And then we have the predict class labels for valid pixels ready as well. Also, we have the reshaped part of the code where we shaped it back to the rows and columns. All right, so everything is completed. Although this took more time than I expected, but it's fine. We're ready to go. Next is to go ahead to visualize the classification results from our GMM. So we have the matplotlib.pyplot as PLT imported. We have the listed color map as well, which we want to use to customize the colors for the 5 classes. So as you can see, we have 1, 2, 3, 4, 5 colors. These colors correspond to the number of classes we have right here, 5 number of classes. So we have the fixed size for the size of our figure. And we have this -1 to mask out our invalid pixels. And so we're going to set them to NaN. And then we also have the mean and max. So for the mean and max, we're going to use for our visualization, we want to set it to our first index, which is 0, and our last index, which is the number of classes -1, that is 4. So we have 5 minus 1, that's going to be 4. And then we have the name for our result, which is GMM Landcover. I want to put the axis off this time around. Okay, let's go ahead and run this code. Awesome. So here is our result, the GMM Landcover result. It was able to differentiate the clean or the clear water from the turbid water. So we have the case 1 water and case 2 water. So you can see that the colors here are different. So it gave them 2 different classes instead of 1, as we saw using K-means. Here you can see that we have this turbid water also here, which is same color as what we have within this delta font. Also the river. The river is same as this because it's turbid. We have the green areas around this forested zone here, which is well captured as well. And we have the orange on top of the mountains. However, we do have like mud built up areas as more than what I expected actually. So because the white areas are the built up areas or constructions, right? One other place is here. I was expecting more vegetation or something else here and not these so much built up like white areas here. However, we're going to go ahead and compare it with the true color image from our original Landsat anyways. All right, so to do that, I'm going to read the bands that we need for true color visualization. First is our red band, our green, and then our blue color. So looking at the bands we have in the folder that we read from the starting of this tutorial, we had band 2 to band 7. Remember, right? And so our first band is band 2, which is the blue color, right? The blue band, I mean. And so that's the first index 0. Our second band is band 3. That's the green one. So the index is 1. And our third band is band 4. And that's index 2. So we're going to bring them in from that stack. And we're going to do the true color stack for our composite RGB, the red, green, and blue. One more thing we need to do is to normalize it. We want to normalize it using the min and max normalization to be able to kind of set the contrast a little bit for us to see the features so that it won't be so dark. So we'll just run this code. Good. We've done that. Now we want to visualize. So I'm going to keep the color map to be same as earlier for the Landcover. Here, I'm going to keep it the same. And so the first map we're going to have here is our true color composite map. We set fixed size to be 12 and 16 because I want to make it bigger this time. And we have our second plot. Which is our Landcover plot. So we're going to see one to the left, one to the right. Let's go ahead and run this. To the left, we have the true color composites. And to the right, we have the GMM classification. Looking at these two images, I could see some similarities and some differences. I will start with the similarities. So here we see that we have clear water, and we have clear water here. However, very close to this land or this delta front, we have the turbid water, which was captured here from this classification. We also have the turbid water up here and was also captured. So this is one advantage of the Gaussian Mixture Model as compared to K-means. And then we have the forested areas in green color, as you can see them, well captured. And also the orange ones on top of the mountain here, you can see them, they are white in color. And like I said earlier, the white area, which is the built up area, is kind of much. You can see here, I was expecting something different here, but that was misclassified. And also around this region, this can be mixed, this can be built up area. These are, as you can see, these ones are like mud. They're like mud flats or something like that. But you can see these ones are misclassified as built up areas or constructions, which are not expected to be there, right? Overall, I would say that GMM did a great job, especially by differentiating the clear water from the turbid water as compared to K-means. However, K-means was actually able to capture this area better. Let's have a quick peek of that K-means. Okay, so here is our K-means. So our K-means, you can see here, got those vegetated areas as compared to GMM. However, it was not able to capture the turbid water. All right, depending on the goal of your research or depending on the goal of your project, I think I would say it would be nice for you to try these two methods and decide which one is going to give you the best results, right? Which one is going to be able to classify your features very well. First, you need to consider your data, right? And then second of all, your study area and also the feature that you're interested in. That's going to guide your decision to know which method you want to apply, as well as what number of classes do you want to get from this classification. So you may want to try number of classes 3, 4, 5, or even 10, and then slowly minimize it if you're able to start capturing those features you're interested in. All right, so that's GMM for unsupervised Landcover on Landsat 8, Band 2 to Band 7. So if this helped, please like, share, and subscribe so you don't miss the next tutorials. All right, I will see you in the next one.